Good morning, everyone. I hope you are doing all right. So we started review for the midterm last class. And our midterm tools, if you are just wondering, it is next class right here in the Zoom. And remember, the video has to be on all the time. So we started review, and so far we talked about, let's say, circular motion, which is basically dynamics in radial direction. And that means if we have something moving in circle or maybe just part of circle, then what do? That being the center of the circle, our one axis is going to be in that direction, and that axis we call radial axis. And we know the acceleration is towards the center when something is moving in circle or part of circle. Okay, so with that, we use this formula. Okay. And then we also talked about work, energy, and conservation of energy. So work, product of force. Remember, work is done by a force, or we can find net force and find the work done by net force, or we can find the work done by individual forces and add them together to find the net work done. So work is done by force. So to write the work, we write product of the force that's doing the work times the displacement caused by the application of force and times the cosine of angle between them. This is important. And that gives the sine of the work done. So we don't use sine of this. No sine. Sine comes from here. The angle determines the sine, and of course the value as well. So that's why it's always important that we figure out what angle is the angle between force and displacement. Okay, so only that one goes there, not any other angle you see, not that, only the angle between force and displacement. Okay, so that is work and transfer of work is energy. So energy can be of two kinds. One, kinetic energy, which is energy in motion. So that means if object has mass m and speed v, then it has a kinetic energy. But if its speed is zero, kinetic energy is zero. So that means kinetic energy appears only when something is in motion, okay, moving. So if it is at rest, no kinetic energy, but object can have energy even when it's not moving. We call that potential energy. And by the way, kinetic energy, we've been writing that as a uppercase K. Potential energy, it is due to the position higher from some reference point. So we denote potential energy. So actually this is gravitational potential energy. Now we have to be a bit careful because we also learn about another kind of potential energy, right? So gravitational potential energy, or U with subscript G. So that gives you, that is the product of mass, acceleration due to gravity, and its position higher from some reference point. Okay. This is position from some, or chosen, I should say. And we also learn about elastic potential energy. Stretch. Or compression. And then third thing we learned was conservation of energy. Oh, it is part of that. So let's just write conservation of energy. So when friction is not present, so conservation of energy is basically total final energy is equal to total initial energy. Okay. So when friction is not there, is zero. That means when there are no non-conservative forces, we can write that as a sum of just the kinetic and potential, also called mechanical energy, right? So we just repeat this. But when friction is present, we write work done by that friction force, or we also call that non-conservative force, is equal to change in kinetic energy plus change in potential energy. And you can expand that like this. This change in kinetic energy means half mBf squared minus half mbi squared. And then change in potential energy means mgyf minus mgyi. So that is about the energy and work. And we also talked about power. Power is a rate of energy transfer or work done. Okay. So we write the equation by writing change in energy over time interval. And change in energy could be coming from change in kinetic energy plus change in potential energy. And then over time interval is there. So regarding power, I have a question for you. Get ready with your clicker, and looks like I haven't started clicker yet, so I'm going to start that one. So here object goes from 0 velocity to v velocity. So change in velocity is just v. Over here it goes from 0 to 2 times v. So that means change in velocity is 2 times v as well. And we learned that power is change in kinetic energy plus change in potential energy over time interval, rate of transfer of energy. So in this case, this is 0 because vertical position is not changing. The car is not going up and down or something like that. So since kinetic energy is half mv squared, change in kinetic energy comes from change in velocity. Mass is not changing, so it means it has to just come from change in velocity. So that means it's going to be change in velocity squared. And there is time interval. So in this case, it says power output of the engine is same. So power is fixed. So that means the velocity is changing. So that changes in velocity has to be compensated by change in time interval to keep the power constant, right? So for example, if you have something like this, 8 is 16 over 2. Now let's say the 16 becomes 4, 16 becomes 32 times 2, then this is not constant anymore. It's not 8, it is 16. So to keep it constant, you need to change this denominator by the same proportion, right? So denominator has to increase by same proportion as the numerator increased so that the result remains same. So now still this factor is still same. So similar idea can be used to answer this question. And I am letting you to do that. And you have total 2 minutes. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got 3, and C has a majority. Oh, is that it is the right answer? So let's see, how do I get that? So here, delta V was just V here, but this is 2V. So this equation has delta V squared, not just delta V. So that means delta V squared here going to be just V squared. But delta V squared here going to be, this whole thing is squared means 4 times V squared. So now we have this V squared and V squared. What changed? This factor 4. Okay. So it takes 4 times more time to double the speed. It takes 4 times more time to double the speed. So original time is 2 seconds. So 4 times of 2 is 8 seconds. So yeah, looks like it is a correct answer in this case. Okay, so with work and energy comes the momentum. After that, work, energy, and power. So comes the momentum. And momentum is a vector, and it is defined as product of mass and velocity. So here I'm writing this to emphasize that it is vector quantity. So direction of momentum is determined by the direction of velocity. And we also defined another quantity called impulse. It is product of force and time interval. But force may not be always constant. If force is changing, then what do? Is we write the average force times time interval. Okay. Sometimes we may be given this impulse in terms of a graph like force and time graph. Okay. So when it is given in terms of graph, then impulse is area under the graph. Do not use this definition, okay, when impulse is given in terms of graph. Rather, always find area under the graph. So this and that gonna be same only if the force is constant here, okay, as in this case. But if force is not constant, it's going higher, coming lower, something like that, then if you use this product of force and time for the impulse, this is going to be incorrect. Okay. So when you are given force that is changing with time and it is given as a graph, then how do you find impulse? By using area under the graph. Okay. So that's what you need to do. And why that is important? So impulse can also be related to, impulse is related to change in momentum as well. So that helps us to basically solve some problems. And here is one such example. Okay. So over here you see I'm finding the impulse, and then I'm using area under the graph as change in momentum. So whenever you need, you can write area under the graph, which gives you impulse, and it can be positive or negative depending on which side the force is, positive side or negative side. And at the same time, change in momentum means final momentum minus initial momentum, that is change. Or you can write in terms of mass and velocity. product of mass and velocity, something like this. So this gives us this gateway of calculating the velocities from impulse, okay? So that's how it is related. So if force, time interval, and velocities are given or asked to calculate, then you can use this idea of impulse is equal to change in momentum thingy, okay? So change in momentum can be found by, through the impulse, but sometimes you may be given just the momentum vector, pi, pf, and nothing else. In that case, you have to use those two steps method of drawing, right? Finding the difference in vector, okay? And that's what this example is about. So over here, we see there are two momenta are given, and you are asked to find impulse. So since impulse is also equal to change in momentum, since the momentum are given vector, notation or vector drawings, or vector, the momentum are given in terms of vector representation here by drawing the line with arrow. So you can use this idea of impulse is equal to change in momentum to answer this question. And change in momentum also means final minus initial. So that means you are subtracting two vectors or finding the difference between them. So for that, we use two steps method. One tells together in short. The details with the examples are in my note. We did that in class as well. And we draw change from tip of initial to tip of final. So these two main steps, although I have written this is in 3 steps in the note. So these are two main steps. So with this information, I'll let you do it and pull, and you have a minute and 30 seconds. Go ahead, draw the change, double check, change answer if needed. Thirty more seconds. And 5 more. Oh, 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So tails together, first draw tails together. So you can move tail of this one to the tail of this, or other way around, either way is fine. So over here, I'm just moving something like this. So that means I'm just moving this one over there. So this is my new position of the pi. Vector is still same because I did not change the direction. I did not change the length. Okay, so that is step one. And in step two, draw a change from tip of initial. So initial is this one. So tip of initial is here to the tip of finals. That's that. So that gives me change. And that means A is correct answer in this case. Okay. So most of you did it correctly. Or other way around, if I were to move tail over here, then I would be drawing something like that. That is PI. So tip of PI is here, so I'm drawing that. Delta P, still same. No wonder. And if you did this one here, that means you are not subtracting, you are adding, okay? PI plus PF, that's what that is, but we are looking for PF minus PI, totally different thing. So if you are bringing tail to the tips first, rather than tails together, and then drawing from the tail, starting from the tail of the very first you drew to the tip of the final, that is the method of adding two vectors, okay? Not subtracting. So that's why this is not correct. Okay, so now there is another question related to momentum and impulse. So here are some related formula. Although I said momentum and impulse, looks like this question is talking about kinetic energy. See, the kinetic energy has half mv square, momentum has mv, so they are closely related, okay? They are closely related. They both come from a product of mass and velocity. One has velocity squared, another one has just velocity, okay? So here we are asked to find kinetic energy of light card. Kinetic energy equation is here. So mass is given, but are we given the speed? Okay. So we learn in class, and I emphasize a lot, that if both of these are not known, then using this equation may result into incorrect answer, right? That's not a good idea. So that's why these may be helpful to come up with the relationship between mass and velocity, and that way eventually you can use it. So it's going to be two-step process, okay? So that's why I'm giving you 3 minutes to do this problem. So go ahead, do it, choose it, and change it if needed. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So just like I said, if I just use the mass information, bigger mass, double mass means double kinetic energy. If I were to do that without knowing the speed, then that is not the way to do it, because we don't know about the speed. There is no information about the speed here, okay? But there are other information. For example, time interval is given, and that is same for both. Force is same for both. And initial velocity is 0 for both. So initial velocity 0 means initial momentum is also 0. So final momentum is just then force average times time interval. And since both of these are same for both of, same for each of those, so final momentum is same. Although they have different mass, the momentum is same. What does that mean? We know momentum is product of mass times velocity. So if mass is double, then velocity has to be half to keep the momentum same. So now we have some idea about the speed. When mass doubles, speed becomes half in this case, because this impulse is same for both of them. Okay. So that means although you are applying same force for same time interval, the smaller mass is moving with higher speed now than the larger mass. By how much? Exactly double. Small mass is moving with exactly double speed. So now we can do the kinetic energy for these masses, and it says kinetic energy of light card. So if kinetic energy of light card, light card has mass m, and speed we said was, I don't know, did we say v? Okay, let's say that was v. Then we can write that for the light. Now let's do that for the heavy one. Half is same for both. Mass now doubled because it's a heavy, but the speed became half. And remember, this one has to be squared. Okay. So now the mass is there, half is there. So I'll just keep that half because we are comparing, right? So I'll just keep that half. I'll keep the mass because there is mass. And remember, this is v squared over 4. So I have now 2, and there is v squared over 4. Okay. Or I can say now this is, there is half m and v squared, but there is this 2 in the bottom. So kinetic energy of heavy is half compared to kinetic energy of bigger. Sorry, yes, kinetic energy of half is, sorry, kinetic energy of heavier one is half compared to kinetic energy of lighter one. So that means kinetic energy of lighter is 2 times larger than the heavier one, right? Heavy has a half means lighter has a double. So that means it has kinetic energy double. Although it has smaller mass, what happens? Its kinetic energy double because the speed basically doubled, okay? Although the mass is half, the kinetic energy doubled because the speed doubled. That's how it worked out, okay? So that means B is correct answer in this case. So yes, it is a little bit complicated, but it allowed us to review this idea about impulse momentum theorem and momentum, kinetic energy, and relationship between momentum and kinetic energy. So this is a very good question for the review of the idea. Okay. So now we're gonna move to the change in momentum and impulse I was talking about. And remember, impulse can also be written as area under the graph. Okay. So with that said, I'm gonna open the poll and let you work on this. And you have 2.5 minutes for this. And by the way, this is force time graph. And initial direction is positive, let's say. Maybe I should say velocity. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. Mostly B, but we got all of them. Do I know the answer? So mass is 1 kilogram. That is written right there. And if initial speed means vi or velocity, it says positive 4 meter per second. So whatever initial direction it is moving, we are assuming that as a positive. So that means the force is acting in opposite direction of initial motion, right? So it is asking for the final speed. What else do we know? We are given impulse, given as a graph, ft graph. So that means impulse is area under so that means area of the triangle in this case. And area of triangle is half base times height. So in this case, base is 1 second and height is -2 Newton. So that makes it -1 meter per second. Not just meter per second, but kilogram meter per second, I think, unit of impulse. How do we do that? Remember, Newton means kilogram meter over second square. So 1 of the second cancels with this, leaving just 1 second here. Okay. So that is impulse known. So now using momentum relationship, change in momentum is impulse. That means MBF minus MBI is the area. So MBF is MBI. See, this is negative. When it goes to the other side, becomes positive, plus area or impulse that we calculated, right? So VF is now VI because this mass cancels. So now we can use VI as a positive 4 meters per second. And this area was -1 kilogram meter per second. And mass is 1 kilogram. So this kilogram and kilogram cancels, giving us how much? Positive 3 meters per second. So this brief impulse only slowed down the speed by 1 meter per second. It is still moving to the right, but bit slowed down because of this impulse. By how much? By exactly this. So did I calculate that correctly? Triangle base times height, half base times height. Okay. height is this one here, so negative 2 Newton. So looks like it is just negative 1, okay? So it is positive 3, okay? Not positive 2, just like many of you did. Or did I make some mistake here? Did you notice any mistake here? A lot of you made mistake. So what happened here? So one obvious thing might have happened is you just multiplied force and time. So 2 times 1 is negative 2, right? So you use that negative 2 here, and that negative 2 gives you just 2, not 4. Sorry, 3. So what went wrong? Rather than finding area under, you simply multiplied force and time. So that's what I was talking about. Please don't just multiply force and time to get the impulse when it is given in terms of a graph. Okay? Here, force is not constant. So that definition works only when force is constant. Otherwise, you have to use average force. Okay? An average in this case would be negative 1 Newton. So now, in that case, negative 1 times 1 becomes negative 1. So that is brings the 3. Okay? So that is a little bit that mistake there. So anything you like to ask here? Okay, it looks like we don't have question. So moving on. So after momentum and impulse, we learn about conservation of momentum, or also called linear momentum, because now we know about the rotational momentum or angular momentum, right? So this is about linear momentum and its conservation, right? So conservation of linear momentum is final momentum is equal to initial momentum if net force, net outside force or net force on the system is equal to 0. Okay? So that's the conservation of momentum. So you see there is final and initial, like in case of conservation of energy. So we need to label things accordingly, especially the velocities, right? So here I have written before collision, and that is initial situation. Anything that happens before collision is initial situation. So in case of collision, you can use impulse momentum theorem if force or time interval are there. But if it is collision problem and force and time interval are not there, then you need to use conservation of momentum. And to use conservation of momentum, just like we did for the conservation of energy, we need initial and final situation. Here, initial situation is this. And since the conservation of momentum does not involve the vertical position here, we don't need a reference point because it's taking place along the same position. So height is not changing, okay? If height changes, then we need to use conservation of energy idea. Here, that's not happening. So here, initial velocity of mass 2 so here, one with mass 0.2 kilogram, another 1.2, right? So both of these are balls, and one with the larger mass, we are saying that is 2 subscript, okay? So ball number 1 and ball number 2, and we want to list them like that, okay? So these velocities, to include direction of velocity, we need positive or negative sign, and for that, we need to assume which side is positive. Here I am using the obvious choice, positive is to the right, okay? So once you list all these, then this conservation of momentum can be expanded into this, and I think this is also in the formula sheet, okay? And then you plug in and you solve for the things that you are looking for. So I'll be asking you this conservation, principle question. So if you need, copy this so that you can use it. And I have always asked you, especially in the beginning of semester, keep one printed page of that equation sheet that I have posted on Canvas with you while doing physics, okay? So when preparing for the test, do the same. Can you answer all the question using the just formula sheet or the equation sheet? If you can, then you are prepared, okay? And best way to prepare for these exam, to do the worksheets, the blank worksheet. Don't look at my feedback. Don't look at what you did. Just take the blank worksheet and do them fully and see if you can fully understand them. If you do, then most likely you are ready to take tests. Otherwise, keep practicing, okay? So that's one way to check it. Okay, so with that, I am now bringing this question to you. And for this, you have 2.5 minutes. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do. We have mostly B. Okay, so I said block is 1 and bullet is 2, but you can also say bullet is 1, block is 2. Either way is fine, right? So it has mass m. So initial velocity of block is 0. B2I is B, I already wrote. So now what happens? So this is before or initial. Then what happens? Collision happens. And we cannot use conservation of momentum or just the moment of the collision. For collision, what's happening? We need to use the impulse and change in momentum, okay? But this is about before and after collision. So after, what's happening? The bullet is now inside the block. It lodges. So that means both of them are now moving with the same velocity. So final velocity of object 1 and final velocity, oh, I should be consistent. So final velocity of object 2 and final velocity of object 1, both of them are same. So we can write that, or we can just write BF, because after lodging they are moving with the same velocity, right? So once we have that, we can write that conservation of momentum, PF, PI, expand that. So M1, B1, F plus M2, B2, F. So total final is equal to total initial. So I just repeat them with F replaced by initial. So now with this, I see B1I is 0. Initial velocity of block is 0. So now we have these three things. Out of these three things, on the left-hand side, we have final velocities. And we learned that both of these final velocities are same. And we decided to write that as BF. And that's what we are looking for. Okay. So I can write M1. And since this is just BF, and I think I can also start plugging in the M1. So what is my M1? This is M. What is M2? Oh, B1F is BF, let's say. And this is M, BF. Okay. M2 is lowercase m. And on this side, M2 is lowercase m. And then B, 2I is just B. Okay. So we are looking for BF, and BF is here. So we need to factor BF out. And we have M plus M, and that is MV. So BF looks like gonna be MV over M plus M. Oh, that's uppercase, not lowercase. Otherwise, that was close. So that means our answer in this case is E, correct answer. Okay. So most of you chose B. Yeah, that was close, but it is missing that lowercase m here. Okay. So unfortunately, we have to write that as the correct answer in this case. Okay. So I see what I went wrong here. So you thought, okay, maybe that's a typo. If that's the case, then you have to choose this one, right? Okay, maybe we could use a break at this point. So let's take a break and I'll see you in 5 minutes, okay? Welcome back. So after momentum and conservation of momentum, we started, basically that was the basic physics, right? Kinematics, dynamics, and conservation principles. So conservation principles, we learned two of them, conservation of energy and conservation of momentum. So that's the basic physics. And then we move to the application of that basic physics for rotational motion, where object could be spinning and moving at the same time, right? So that's what we did. And for rotational motion, it's not just the force that matters. We learned that at what angle the force is acting matters, and how far it is from the axis of rotation matters. So to take account of that, we defined a term called torque. Torque is defined, basic definition of torque is product of the radial distance or position from the axis of rotation times force times the sine of angle between them. Okay, so this is the angle between R and F. Not any angle, but between R and F. So here we are getting torque as a vector. And to write it in the equation, for the direction, we use, okay, if it is trying to rotate something clockwise, we use that torque as a negative. But if it is trying to rotate all the way around, then we take that as a positive counterclockwise. Okay, so these are just for writing the equations to use dynamics. Okay, but we learned that torque and all these quantities like angular velocity, angular momentum, angular acceleration, including torque, they have actual physical direction. And for that, we need to start by using right-hand rule on the angular velocity. And that way we can figure out the direction of angular momentum, angular acceleration, and the torque as well. Okay. So this convention we are using just to use that in the equation while using this Newton's second law, net torque is equal to rotational inertia times acceleration. So to write this, we're going to be adding torques, right? So torque number one, torque number two, and so on and so on, okay? So while doing that, they're gonna have they have direction means we need to write either positive or negative sign. So for that, we are making this assumption. But these quantities, they have actual physical direction that we need to figure out. But before we figure out direction, we need to also learn how to find value. Okay. So how do we find value? So for most of the case, what we did was we used this formula. Torque is lever arm times the force. Okay. So to find lever arm, you need to go through certain drawings. Okay. And over here, let's say if I'm trying to find torque due to this force acting at a distance r from the axis of rotation, then you go through these three steps that I taught in the class as well. It is in that video or it is in the note here as well. Okay. So here this force is the weight of the board I'm saying, but this branch is already thick enough, but I'm neglecting the weight of the branch there. Okay. So in first step, you know, you make this longer here. The force, whatever direction the force is acting, you make it longer. And then you draw the lever arm, which is the shortest distance from axis of rotation to the line of action of force. So this is going to be the shortest. If you draw here, it's going to be not the shortest one, not those. So by doing this, it becomes shortest when this angle is 90 degree. So that makes this construction a right triangle. So once we have that, what happens is we can now use the trigonometry to figure out this in terms of given angle. So depending on what angle is given, if this angle is given, this is going to be opposite and it's going to pick up sine theta, let's say, if that angle is theta. But if this angle is given, then this is going to be adjacent, means it's going to pick up cosine. So the lever arm going to be r sine or r cosine, depending on which angle is known, right? So we go through that. One case where the force is perpendicular to the r. So that means the angle is 90 degree. So if the force is acting something like that, then the torque is r times a perpendicular component. So in that case, what happens is this r is the lever arm. So because of that, we can just write that as lever arm times force, okay? Or simply say r times f. If it is not perpendicular, you can find its perpendicular component. For example, if this angle is given, rather than the angle between r and f, then you find its component and then use that component here. So there are three different ways you can find the torque. We spent a lot of time talking about that in class, and the last worksheet was about, past question on that worksheet was using those three different ways to calculate, torque, okay? So here I have a question for you. Oops. Now how do I fix that? So I need to exit from here, okay? So all those three things, three methods I have written in words, just in case if that's helpful for you. Okay. So here this angle is given. So based on what you know, how to find torque, find it using any of the method that is most convenient for you and choose the answer. Okay. And you have 2 minutes to answer this question. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. We have C and E competing. So what's the difference? Sine versus cosine, right? So I'll show you all three different methods of calculating here in this example, right? So if you are using this formula, this has to be angle between R and F, okay? So that has to be angle between R and F. Given angle here, theta, is not the angle between R and F. So that's why this is not going to be correct answer. Okay, yes, that is formula, but that is true only when given angle is the angle between R and F. Okay, in this case, clearly you can see this is not the angle between R and F. What is angle between R and F? So for example, here we're saying that is, perpendicular line here by indicating this is 90 degree. So if that's the case, this is going to be 90 minus theta. So yes, then you have to use this RF sine 90 minus theta. And this trig function, of course, I haven't talked here, but if you remember, that is cosine. So it's going to be RF cosine theta. So that's one way to look at it. Okay. Another way to look at it, this is angle between R and F. What is that? That is theta plus 90 degree or 90 plus theta degree. So here you have to use 90 plus theta instead of 90 minus theta, but both gives you cosine, okay? You are just shifting the sine function by 90 degree means quarter cycle, that gives you cosine. Now, this is one way to do it. Another way, so let me leave this right here, it's going to be handy. Another way, the radial vector times the perpendicular component of the force, that means R times F perpendicular. So let's find the perpendicular component of F. So if we go like that and go like that, see, this is the perpendicular component of F, perpendicular compared to the R. So this is going to be adjacent. So this is going to be F cosine theta. So if you plug that in for F perpendicular, then you get this, right? This, both method gives you this. And third method is using the, finding the lever arm. So let's do that one as well. So for that, we have axis of rotation marked already. So now what we can do is we can make this force longer, means draw a line of action of force, or LOF, line of force in short. And then draw a lever arm, starting from where? Axis of rotation to the line of action of force, and it has to be shortest. So it's gonna go something like that. That makes 90 degree here, okay? So this is lever arm. So I'm planning to use this formula, lever arm times force. So this is lever arm, so I need to find that, okay? So now, the given angle is theta. So this angle is 90 degree. This is 90 minus theta, means this must be theta. This must be theta. And now that gives you this as an adjacent. And that's how it picks the cosine component of r. And the torque becomes r cosine theta times f, which is same as this. All three different methods here. So E is correct answer in this case. Okay. Anything you like to add or ask? Okay, then let's move on. So comes the kinematic equations, and these kinematic equation for rotational motion, just like the kinematic equation for translational motion we had, right? So basically these are just the rotational counterpart. And of course, when we use this, we write in a particular direction, in the x direction or y direction. So we put subscript for the vectors. Here, we are just using that sign clockwise and counterclockwise for the, rotation. So there is no motion in the x direction or y direction to say. So that's why we don't see that subscript over there, okay? Just that. So that's the kinematic equation. And here is a question. So to solve kinematic equation, what do we do? Just like any solving any problem, we sketch the situation and we note down the things that we know and note down the things that we are looking for. And then based on that, we choose one most suitable equation. If possible, we just solve with that equation. If not, we may have to use two equations, right? So that's the way to use kinematics to solve problem. So in this case, it says how many revolution. So over here, there is no number of revolution. And just like we talked during the class, if you want number of revolution, you can use this equation, but this may be a little bit confusing. So let's not count as kinematic equation, okay? So with that said, now I'm going to open the poll and you have 2 minutes to pick the equation. Once you pick equation, physics is done. Only mathematics remains. Thirty more seconds. and 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. We got all of them, bit more for B. So in this case, we are looking for N, and that comes from delta theta. Okay. So I should write delta theta. And it says starting from rest, omega I is 0. And the angular acceleration is given. And then time interval is given. And we are asked to find, let's say, delta theta. So this equation does not have delta theta, so we don't use that. So now this one has delta theta, and this one has delta theta. To use this, we need this. We don't know. And we don't care, because it's not asking us to find final speed. So because of that, we don't use that. So now let's see if we can use this here, delta theta, great. Omega I, delta t, yes, omega I is 0, so we can do that. Alpha is known, time interval is known, so that means we can use this equation to find delta theta, okay? So looks like B is the best choice in this case. So once you have that, you can do this. Since initial velocity is 0, it is just half alpha times time interval square. So half alpha is 0.5 radian over second square, time 30 seconds, so 30 square, and second square, the second square cancels. So you get radians. So there is half, that's a quarter. So quarter of 900 radians. Okay. Is that 225 radians? So now number of rotation is delta theta over 2 pi, and that is 225. Divide that by 2 times pi is 3.14. So that should give you number of revolution. So number of revolution could be like complete number like 10, and if it says 10.6, that means it completed 10 and then 60% of the next or 11th rotation and so on, right? So that is about using kinematic equation for rotational motion. How about dynamics? So here is a question. In dynamics, Newton's second law for rotational motion is written as net torque is rotational inertia times angular acceleration. So in this case, this is in equilibrium. So here acceleration is 0, means net torque is 0. So how do I find net torque? So torque comes from the force. So there are 3 forces acting here. One force on the feet, another force on there, and the center of gravity, there is this mg. So we draw free body diagram. Here we are drawing, so object of interest here is portion, so we replace portion by a straight line, okay? And then we have F2 going up, F1 also going up, but the mg is coming down. That's the weight of the portion, okay? It's always acts vertically down. So these forces are perpendicular to the portion, at least approximately. So we need, so that means we can find torque by lever arm times F. So before we can decide which lever arm, what is lever arm, or how do we, find the lever arm, we need axis of rotation. So this is not rotating at all. So we can choose axis of rotation anywhere that is convenient for us to solve this problem. So in this case, we are asked to find the F1. So we need this. So if we choose axis over here, it's going to be gone. So we cannot find that by choosing axis there. So this is not a good choice to choose axis. Okay, not a good choice for the axis. The F1, where the F1 is acting. mg, see the mass is known. So this, if we choose axis over there, we're going to be eliminating the quantity or the force that we know. Not a good choice. On the other hand, F2 is a good choice for the axis because this F2 is the one that we don't know and we don't care. We're not trying to find F2. Question is not asking us to find that. So we want to eliminate. We don't know that, so we want to eliminate that. So if we choose axis there, that's how we can eliminate that nicely. So now lever arm going to be always the shortest distance from the axis of rotation to the line of action. So over here, this whole thing going to be L1, okay? And let's say this is L2, okay? mg, lever arm for mg is L2, okay? So once we have that, now we are ready to write this equilibrium condition, net torque, 0. So now there are two forces that are providing the torque. One is F1, another one is mg. Remember, we already eliminated F2 by choosing axis over there because if the axis is right there, then lever arm going to be 0 for this force, means torque going to be 0 as well. So for this choice of axis, torque due to F2 is 0, so we don't worry about it. That's why we chose axis over there. So now torque due to F1, let's talk about that. So it is trying to rotate this way since the axis is there. So that is counterclockwise. Oh, not counter, just clockwise, okay? And then that is negative. So sine of the torque is negative. And what's the value of torque? It is lever arm times the force itself, so L1, 1. Now, we repeat that for mg. So mg is the force. And now, since the axis is over there, it's trying to rotate this way, means it is counterclockwise. So that means its sign going to be positive. So what's the value of torque? It is lever arm, which is L2 we are saying, times the force. So that is the sum of torque. So two forces are providing torque, and we wrote the torque of these two forces. So that must be equal to, now let's copy the right hand side, which is 0. And in this case, we are trying to figure out what is F1. So F1 is, so let's do some rearrangement here. So it looks like it's going to be L2 mg over L1. Okay. So we know M, we know G. Do we know L1? Do we know L2? L1 as this, based on what we chose, it is all the way. So that means this is whole length, means it is 1.70 meters. Okay. And L2 is this from feet to the center of gravity, means weight. So that is just 1 meter. Okay. And of course, the mass is given 68 kilogram. And G, we can use 10 or 9.8. These numbers are given here, and it's just asking for approximate value. So I'll just use 10, but you can use 9.8 if you like. But I think for me, multiplying that going to be easier that way, right? Okay, so now we plug in the values. L2 is just 1 meter, and L1 is 1.70 meter, and then M 68, and let's say 10. Okay, there was kilogram. So kilogram here, meter over second square over there. So basically that gives you a Newton. This cancels, right? So 680 divided by 1.7. Oh, did I pull on this one or just kept doing, looks like? Oh. So 680, 1.7, looks like this F1 is closest one. It looks like I did not pull on this, did I? Nope. I did not stop. And by the way, worksheet number 2 was basically the same question on question number 2 on last worksheet number 9, I think. Okay. The same question. It was basically same question. So looks like that is correct answer for that, but I forgot to poll on that. I did not open the poll. And let's say if now you have to find F1, you can use just translational equilibrium condition. And for that, we need to make new free body diagram. And I noticed while grading, many of you did not make this free body diagram. So whenever you are using this formula, let's say you need this free body diagram, not this, okay? So both of these are positive. So F1, F2, and mg is negative, is 0. So F2 is mg minus F1. So that's how you can calculate that force if needed. But in this question, you are not being asked to find that, okay? So again, this was question number 2 in the last worksheet. Okay, so now with that, I spent too much time on that. So now here it is pulley, and this mass is there, and it can unwind because of this mass here. So there is, this thing is coming down with acceleration A. So now question is, what is the acceleration of this mass? Okay, so it is like a now elevator problem. Okay, you want to make free body diagram of this. See, the tension is there. and weight is there, and you can find the tension. So use Newton's second law, sum of forces along the y direction 0, and pull on it. So you have 1 minute and 30 seconds for this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, it looks like what we got here. So we got all of them, except, let's see, a little bit more for B. So sum of forces, oh, not 0. In this case, it is accelerating. So maybe I should have written this. So T positive, let's say, assuming up as a positive Y, and then mg is negative. The acceleration is also pointing down, so it's going to be negative ma. So t going to be positive mg minus ma. So yes, looks like B is correct in this case. So now we did this because this is needed to solve part B. Okay. So here, what's happening? There is axis over there. So it is falling down. So that means there is this tension force making this thing spin. So now the question is, what is torque? So tension was mg minus ma or something like that. So I'm letting you pull on this, and you have only, let's say, 30 seconds to pull on this. So you are asked to find torque. Torque is lever arm times force. Five more seconds. 5, 4, 3, 2, 1, and it stops. So we mostly got B, and that is correct answer because lever arm in this case is just R. So that means torque is L times F. F is tension force, and this lever arm is R. So that's why that is correct answer. And we talked about conservation of energy, and which is same as, the linear case. Only new thing is this quantity rotational kinetic energy, right? So we ran out of time, so I'm going to just leave it here. There are a couple more slides, and those things we have done in the class. So if you need that to review go watch video, okay? For example, we had a question like this before during the class, and we went through this, how the direction works in the class. For example, how to use right-hand rule to find direction of angular velocity. Once you have angular velocity and know it is increasing or decreasing, you can figure out the direction of these, right? So that's it, folks. So I'll see you in next class for the test.